Hey physicists, we're going to do a quick review of our constant velocity motion. We can represent that motion with two different types of graph, the position versus time graph or the velocity versus time graph. We looked at a little bit of that in our last class. Let's first take a look at forward motion moving at a steady pace. On the position graph, we would end up seeing it looking something like that, a straight line with a constant positive slope. For velocity, what we'd find out is, I'll mark this as being 0 here, because our velocity stays the same, there's no change in the velocity with time. We would see something that looked like that. Let's take a look at the special case of zero velocity. With zero velocity, I'm standing still, so we see that our position stays the same as time goes along. What we'd also find is that our velocity, another way of saying that, is that velocity is 0. I'm drawing it just slightly above the 0 line. You can also draw a little bit below, just to show it's right on the line. Okay. So our position stays the same when we have 0 velocity, and our velocity stays the same at 0. Hey, the last constant velocity motion we'll look at is negative velocity, or an object moving backward. On our position versus time graph, we would see that an object would start at with a greater position and move to a lesser position. Taking a look at the slope of that, that now has a negative slope. For our velocity, we would see that the velocity remains the same, but it is negative. Another way of tracking motion is with something called a motion map. A motion map records the position of an object as it moves at some regular time interval, customarily 1 second. Let's take a look at this car as it moves along. You'll see that it drips oil out of the engine about once every second, so we have a record of where it was each second. Hey, so here we have our bug dropping a drop of oil each second, and gives us a record of where the object was. We can add in some direction by just adding in some arrows that indicate which direction it was going. So the idea is to draw from one arrow to the next to let us know how far it's moved since the last drop of oil. And to let us know when that happened, we can put the time that it occurred. It started here after 1 second, 2 seconds, and 3 seconds. This is a motion map to give us an idea how the bug was moving as it went across the screen. Okay, so that method works fine if our object is moving from left to right, but how would we end up recording motion if we're moving from right to left, which by convention we'll call the negative velocity. We'll go ahead and we've got this little Zamboni going across, and it's going to move from right to left. See, it's moving a little faster than our bug here, okay, and we've ended up dropping dots of oil. I guess drops of oil on the ice, but a drop of oil once each second here. Let's see how we'd end up drawing this as well. So let's go ahead and draw in arrows that will represent the movement of the Zamboni between the drops of oil. So I have an arrow now moving from right to left, from right to left. The last one we don't quite have it. This is going to be at a time of 0, 1, and 2. The length of the arrows indicate how long it has moved since the last time we dropped oil, so we can see that the length of the arrow represents how fast it was moving. Hey, so we're going to look at a motion of a bug across the screen, and we're going to go to make a motion map, then a position versus time graph, and then a velocity graph from that motion. So take a look how the bug moves here. There we go. And it moves at pretty much a constant speed from left to right. Here we're going to change this, so we're going to go ahead and make the motion map. Okay, so now let's take a look at the bug as it moves. We'll drop a oil drop out the back of the bug once a second or so. And here we go. So these dots will transfer over to a more generic, let's see, motion map. Okay, so I'll put dots representing the motion of the bug. Right, hold on. It's gonna be a little bit tricky. I'm bringing something up. Okay. Hey, so the bug was moving from left to right, and in 16 seconds it covered about 40 meters. I just showed the first 10 seconds where effectively the oil drops would end up falling. Okay, I'll put in my arrows showing how much it moved between each of those ink spots. I guess we could call it that. The longer the arrows, the greater the velocity it represents. Okay, I put along here. I know it was going about 40 meters in 16 seconds. That works out to about 2.5 meters per second. You can see that, or another way of saying it is that it takes about 2 seconds to go 5 meters. Okay, next thing I want to transfer that information over to the position versus time axis. Something you'll see pretty often is that instead of position, the term x is used in physics. Yep, so often x is used for position. That's one of the reasons why we don't call it the x-axis, because often x ends up getting labeled on the vertical axis. All right, hey, so for my position, my time, I'm going to label this in 2-second increments, 2, 4, 6, 8, 10. That'll cover at least as much as we have there, 12 and 14 seconds. You know, move along this axis. We want to get at least 25 meters in there. So it goes 0, 5, 10, 15, 20, 25. That's going to cover what we have there. 30, 35. So it covers what we need pretty well there. Hey, I'll put in my spots. At 1 second, I'm at about 2.5 meters. At 2 seconds, at 5. So on. So I end up creating a dot for each of these the spots on the motion map. Okay, I'll put my best fit line through there. Oh, actually, those line up pretty well. Hey, and of course, to figure out the velocity, I want to look at my rise over run. Some of you may prefer y2 minus y1 over x2 minus x1. Be careful of what we call x2 and x1. I want to pick 2 spots on the axis. I'm going to pick this spot. Sorry, 2 spots on the line. That one looks like a good one. And perhaps this one here. Okay, so my rise is going from 10 to 25. So my rise, and it is going up, goes 25 minus 10 meters. My run, let's take a look at that. I'm going from 4 to 10 seconds. The difference of that. So I'll have 15 meters over 6 seconds. That works out to 2.5 meters per second. That's the slope of the line. That also works out to be our velocity. Notice it's a straight line, so that tells us our velocity is constant. Come over here, and I'll pick a mark here. 2.5 meters, maybe up here is 5, and it will end up staying at the same velocity, that same positive velocity. So I've taken that initial motion, I've created a motion map showing a kind of a spot every second where it is. I've gone to a position versus time graph, taken that information and put it into a velocity graph. We'll do another one as an example. So this will be another item on page 2. All right, let's take a look at how we'd produce a motion map, position versus time, and velocity graph if our object was moving the other way. So we'll take the same bug and it's going to go the other direction now. We'll produce a motion map. Moves along, again dropping an ink spot each second as it goes along. Okay, let's go ahead to the motion map and put that together. Hey, again, so I just monitored the first 10 seconds, but if we look carefully at the display, we can see that the bug started at about 40 meters and was moving to the left. We're calling that a, let's say, a less positive position. So our origin's on the left. So I've labeled that. Next thing I want to do is indicate the direction with arrows between those. So let me go ahead and do that. Okay, so you can see I'm putting in these small arrows. But the arrows are just give an example of here. Those arrows are pointing to the left, indicating the direction of motion. They're pretty closely spaced together, so there's not a whole lot of velocity there. Let me pause this and I'll get set up to put position on there. Hey, again, I'm going to label the first 10 seconds. I'll put that on this position versus time graph. Hey, I've made each division 5 meters, so I get all the way to 40 meters. Across the horizontal axis, it looks like 2 seconds per division works best, and I'll start plotting that up at 40. You can see I'm just transferring the points from my motion map onto the graph. Okay, at 6 seconds, I was right at 25. Yep, I've got it there. Out at 10 seconds, I was at 15 meters. You can see that here. Hey, I'm going to go ahead and put a best fit line through. Using my 6-inch ruler. Pass that through there. Not the best straight line, but you get the idea. Okay, and I'll pick 2 points on here to figure out my slope. How about that one at 4 and 30? And this looks like another one kind of right on there. Remember, I'm not picking data points, I'm looking for points on the line. Okay, so I'll do my y2, and our slope is our rise, or in this case, our fall over the run. And so how far are we falling? From 30 down to 15. So 15 minus 30, I fell, in a way of marking that, 15 meters, because it's down. And I went from 4 up to 10 seconds. So 10 minus 4 seconds is equal to 6 seconds. Hey, we get the same slope, negative 2.5 meters per second. Let's go ahead and graph that. Now we can see, because it's a straight line, or somewhat of a straight line, our velocity stays the same. So out here, we're going to be on the negative side here. So at negative 2.5, I start my velocity, and it stays the same all the way along our time. So this is the second example on page 2, and you have a chance to do a few of these to practice motion maps 1, 2, 3, and 4 on page 3. Practice for yourself.